It's a pleasure to be here, and I want to thank the organizers for bringing us here together in this wonderful venue with stimulating discussions. I will talk about manipulation and probing of spin ensembles, and for us, spin ensembles, at least for this talk, means a magnetic systems in the sense of a ferromagnetic systems. In particular, I want to acknowledge my collaborators in this, which is Sebastian Gönnwein, Rudolf Groß, and in particular, Matthias Weiler. He pursued most of the work, or the second half of the talk, during his PhD thesis. He went away to the NIST in Boulder, and we have him now back, luckily, and will continue work in this direction. So what is mechanics or acoustics for us? So for me personally, it starts with basically this picture, which is a guitar, a doubly clamped string, and I will present you some works in this direction. But you can also envisage acoustics in a broader sense. Here, infrasound and atomic force microscopies, applications like gyroscopes, and we all heard about surface acoustic waves in this workshop already. So our motivation in this direction is magnetism and mechanics, how to bring this together, how the coupling works in this scenario. The general idea is then, on the longer goal, is to find quantum effects in these systems, which is typically not used, at least in the field of magnetism and mechanics, in some kind of more general, more typical configuration. So for magnets, you would say, I can describe, at least in a ferromagnet, everything reasonably well with a classical magnetization vector which points in some direction. And for the mechanics, you would say, okay, I'm sitting on a swing, I have an amplitude and a phase, or amplitude and a momentum, and that's it. And the question is, can we get there, and what kind of tricks can we play to push in the quantum direction, in particular for large objects? Okay, we have several acoustics topics at the Walter Meissner Institute presently running. This ranges over a variety of systems, which consists of circuit nanoelectromechanics, where we try to combine doubly clamped strings with microwave resonators and transmons. And this is our latest proposal, combining a doubly clamped string with a transmon qubit, or embedded in a transmon qubit, and couple it to a microwave resonator. And the idea is here to prepare, or being able to prepare, a mechanical Fock state in this doubly clamped string. What I want to talk about today is, as I said, coupling between a magnetic system and mechanics. And I have picked out two examples, a doubly clamped string system and a surface acoustic wave system. Here I want to focus on magnetoelastics and how we can sense the magnetoelastics or use this as a sensor for magnetoelastics. And here I want to pursue the inverse direction using a modulated stress field to drive magnetization dynamics. Okay, I said to you already I'm a fan of acoustics, and therefore I would like to start with this picture. All what you need to know for the first half of the talk basically is that the mechanical frequency of such a doubly clamped string, if you kind of tensely stress it, is given by the inverse length, the stress and the density of the material. And for your violin at home, you would try to tune this stress to tune it up properly. We typically use silicon nitride. That means that we have a fixed stress in the system, and so tuning is done here via length variations, and the frequencies are in the megahertz range, mainly due to the fact that we reduce the length of the string by 4 orders of magnitude. And since I can't hear in the megahertz range, we use a different technique for reading out this out-of-plane motion of this doubly clamped string. And this is, one of it is optical interferometry. So we shine a laser beam onto these strings, and then you could, for example, look at the Brownian motion of the systems. That is doable. What we then for convenience do is we drive a piezoelectric actuator. This creates a force in the sample, and this creates an out-of-plane motion of the string. And if you do this as function of frequency, then you can measure the mechanical response function of this doubly clamped system. What you want to focus is on this mechanical frequency. You could also look at the mechanical line width of this system. But as we want to talk about magnetoelastics and stress, I had already the relation up here. We will kind of monitor the change in this mechanical resonance frequency. So now the stage is set. If you want to do magnetoelastics now, you have basically prepared these strings in silicon nitride, and then it's an easy task to fabricate or kind of deposit any sort of materials on this type of device just by taking it, putting it in your evaporation chamber, and then you have a flexible way of depositing here, for example, cobalt under this doubly clamped beam, and then you're ready to go. I want to remind you in this context on the multiferroic triangle, and because it has a lot to do with the workshop we are having here. For the surface acoustic waves, for example, you would use polarization, electric fields, and then piezoelectricity to drive a lattice motion. What we will do this later in the talk. For the first part, we will focus on the on the baseline of this triangle, where the magnetic field is used to control orientation of magnetization, and then where the inverse magnetoelastic effect controlling the stress in our thin film. And there comes basically the trick. If we have our magnetic thin film on our doubly clamped beam, and we orient the magnetization direction along my right-hand arm, then a cobalt film tries to shrink in this direction, and this creates a stress. And if I now rotate by 90 degrees, the axis tensile stress is still in this direction, but Poisson tells you that I'm pushing now in the orthogonal direction, and this is exactly what I want to do with my beam. I want to control the magnetization direction, and then I can tune with my magnetoelastic component from a bit extra tensile stress to a bit extra compressive stress. And this is what we're going to do. We measure this by, again, looking at this mechanical response spectrum, which you see here. And if you now measure this mechanical response spectrum as function of your magnetic field direction and therefore the magnetization direction, you notice that you see this characteristic oscillating signature. So this is color-coded. The red features are the resonance frequency of your beam. And you notice already, okay, if I have 0 degrees or being aligned along this string, we have relatively high frequencies. That was this extra tensile stress. And if we go to 90 degrees orientation, where magnetization and the long side of the beam is 90 degrees angled, then we have a reduction due to this little bit of extra compressive stress. You can, of course, analyze this in more detail by extracting these resonance frequencies, and you can model this relatively easily with magnetoelasticity. And the trick is basically that you kind of compose now this multi-layer system with your effective stress into a static tensile stress and a stress component which is related to your magnetoelastics. And you can quantify it in the sense that you need to take geometry factors into account, because you have a silicon nitride layer and a cobalt layer on top. These are basically the film thicknesses. Then you have the magnetoelastic constant of your cobalt film in this case, and Young's modulus, or the effective Young's modulus here. And if you kind of compute this, you only have to take into account this frequency change here, and then you can quantify your magnetoelastic constants. And we tried this for a reasonable thick, 10 nanometer thick cobalt film, and get values which you would get from literature, so bulk values. the nice thing is that this method is compatible with thin film technology, so you could go to ultra thin films due to the high quality factors of the silicon nitride beams, and we hope for surprises when going to really monolayer films in this direction. And another key advantage of this technique is that you only need to measure the resonance frequency of your system. You don't need to quantify any bending radius, which is typically done for measuring magnetoelasticity. Only the resonance frequency is a relevant quantity, and this is actually pretty simple to analyze. Okay, I promised, so we have looked at the direction from the magnetization orientation and created stress. The question is now, can we do the inverse thing by changing the magnetization orientation by applying stress? And the answer is yes, we can. And for the upcoming part of the, or second half of this talk, I want to focus on the scenario where we want to drive magnetization dynamics in the system. So what do we need to do then? We have to create a modulation in this stress field, and I think I don't have to say what the obvious answer for this problem is. You need to have a sound wave or eventually a surface acoustic wave. So this will be the drive concept for the following, and we want to let that interact with a precessional motion of our magnetization. And so magnons will come into play. And the idea is to literally put these two things on top of each other. So we glue our ferromagnetic layer on the surface acoustic wave and look at the interaction, the magnon-phonon coupling in this system. We already heard talks about ferromagnetic resonance today. And the advantage of this drive concept could be that the velocity of the surface acoustic wave and the typical propagation velocity of spin waves are rather similar. It's in the kilometer per second range compared to if you drive with a microwave magnetic field, where you have here instead the speed of light. So mode matching is, so to say, a natural thing in these type of structures. So my version of ferromagnetic resonance is as follows. We're talking about a ferromagnet in this case. So we not only have to take an external magnetic field into account, but also demagnetization or magnetic properties of this specimen. And this all boils up in an effective magnetic field. And in equilibrium, the magnetization will align with this effective magnetic field. If you manage to excite this magnetization or create some cone angle, then the Landau-Lifshitz-Gilbert equation tells you that the system will precess with the Larmor frequency, but it also will be damped via this damping term and spiral down to this equilibrium position, giving you the resting case scenarios, the steady state scenario. Okay, what kind of drive options do you have now? You can either do a microwave drive, so an oscillating magnetic field with high frequencies, and you match this resonance frequency with the Larmor precession frequency, and then you can get this finite cone angle here that was talked about today. And we want to focus now on the mechanism, how we can do the same thing with an effective magnetic field, a magnetoelastic magnetic field, which we also drive with this resonance frequency. For this, I want to step one step aside because I want to show you a bit of the theoretical framework behind it. So for this, I want to kind of introduce to you a free energy approach, which tells you about the equilibrium direction of your magnetization and what kind of role the magnetoelastic interaction plays here. Okay. So for this, you take into account your Zeeman interaction in this free energy approach. This is this term you have also, or you want to take into account due to the particular shape or the thin film geometry of your ferromagnet, the so-called shape anisotropy. So this is the order of a Tesla, roughly, and for in-plane you can also model pretty well with an in-plane anisotropy, an uniaxial interplane anisotropy, the whole energetic landscape. And you see already, okay, if I apply magnetic field along the z direction, I will have to overcome the shape anisotropy to guarantee that the magnetization points out of the plane. Or if we have low magnetic fields, then it already tells you that the magnetization want to rest in this plane. We want to introduce now or bring the surface acoustic wave into the concept, and the idea is literally to deposit this magnetic thin film, which should have a magnetoelastic component, onto the surface acoustic wave, and we employed Rayleigh waves for this context. And you see already the typical animation of the surface acoustic wave, and you deposit your green thin film on top by evaporation and modulate now the stress by periodically stretching it and compressing it. So you have a modulation of tensile stress and compressive stress onto your green ferromagnetic balls. And to be honest to you, the film extensions for our films were typically larger than one wavelength. So we have to think more about in this scenario where the surface acoustic wave really is partly compressing and partly stretching the film locally differently. Okay, all what you need to take or keep in mind is we have regions of compressive stress, regions of tensile stress, and I now want to introduce the ferromagnetic or the free energy component, which is related to the magnetoelastic interaction. And so it is proportional to the magnetoelastic coupling constant, which you rephrase in this context in terms of a virtual magnetic field. You have proportionality to the stress or the strain in the system, and this gives you the direction of your surface acoustic wave propagation. So this tells you already that we are selecting here a propagation direction along our x direction. And so you can imagine now the drive concept as follows. We align by external magnetic fields, for example, that the magnetization in equilibrium points along somewhere in the plane. And this uniaxial free energy approach tells you that we want to move now, or we impose this uniaxial anisotropy approach on top of this kind of resting position. Here is my energetically favorable position, so the magnetization wants to tilt a little bit to the left. This is for the case of a positive epsilon. I can invert this now fully by just going for the opposite direction, negative epsilon, and then the magnetization wants to tilt a little bit here to the right. And you see, if I'm doing this kind of quickly enough, I can start moving my precession or my magnetization, and then I will create a resonant excitation here in the system. You also notice that there are some particular directions. So if I have my M0 parallel to X, then I'm already at an extremal point of my uniaxial anisotropy, and therefore drive is inhibited, same as here. So I expect here only strong drive is if the magnetization M0 is somewhere in between the Y and the X direction. Experimentally, the setup is initially rather simple. We start with the conventional IDT structure, have a nickel film in between, and then we have our IDT detector, and we measure the complex microwave transmission through the system. The first harmonic of the system is at 170 megahertz, and then we see higher harmonics in the system, and it actually turns out to be favorable to use higher harmonics or high frequencies for exciting the ferromagnetic resonance. What do you need to do then? You want to investigate the whole thing as function of the magnetic field. That's evident because there you have the tuning capability for adjusting your Lambo precession frequency. So you take, for example, 100 millitesla field as a reference, and then you can kind of record your 9th harmonic spectrum. You tune the system into resonance in a way that you can here excite a precessional motion at 7 millitesla, and then you see a reduction in the transmission. And the reduction is actually not that insignificant. It's roughly 5 dB in this case. You can then convince yourself that this is really a ferromagnetic resonance by looking at this attenuation as function of an externally magnetic field. So this was a data point I showed you before. You go then for 1.5 gigahertz. So this is the 9th harmonic. You ramp your magnetic field. You see this 2 characteristic minima. If you're doing magnetism, you try to also look at the other sweep direction, and you find here the resonance condition for ferromagnetic resonance. You convince yourself even more when you do this as function of frequency. Therefore, you can use multiple harmonics, and you notice that the Larmor precession frequency changes, or the resonance field changes as function of the frequency, and this really convinces you that you are talking about ferromagnetic resonance in this scenario. I talked about the angular dependence of this. What I showed you was the red line. So far, we have analyzed this as a function of the field direction. This is the waterfall plot of the data. You can color code this, and you notice some specific cases at zero angle between, or when the magnetic field is aligned in parallel with the k direction of the surface acoustic wave, you have basically no excitation, and the same is true for 90 degrees. And this free energy approach that I've introduced so far can be actually brought to use in the sense that it allows you to simulate what you should see in your transmission data. So this is the data that I've showed you so far for 1.55 gigahertz. These are the other harmonics. You can look at the complex transmission or at the phase. And if you kind of take this free energy approach serious, then you see that the simulation matches the data rather well. The important thing here is all these parameters are not fit parameters, but you can determine them via other methods, and so they are just kind of, so they are not free fit parameters, and there is no free fit connected to this. Up to now, we have only listened to this sound wave and listened at the attenuation of this sound wave. And then the obvious question is there a way to access directly this ferromagnetic resonance or look at the magnetization precessions in a more direct fashion? And yes, you can do this, and this is called in the magnetism community spin pumping. And what we've discussed so far is that we can excite this precessional motion of this magnetization, for example, with our magnetoelastic field. We can now play the trick and put on top of our ferromagnet a normal metal, and the typical candidate here is platinum. And if you do so, you can relax this angular precession motion, or this in form of an angular current in this normal metal system. So you get a so-called spin current into this normal metal, and this spin current is helpful for you because if you have a spin-dependent scattering mechanism, then you can go for the inverse spin Hall effect and convert this spin current into an orthogonal charge current. Okay, what have we done? We have a precessional motion, a spin current. This is converted to a charge current, and this charge current is proportional to this cone angle here of the magnetization. And we operate our device here not by sensing charges or charge current, but we are using an open configuration, an open circuit configuration, and measure voltage then. So we will look at the direct voltage, which is DC voltage emitted under this drive concept. Then your setup looks a bit more complicated, not really a lot more complicated. Again, you have an IDT for an emitter, a detector, and you have your cobalt platinum stripe now, which you have hooked up to your voltmeter. And as you might imagine, there is some electrical crosstalk which comes in the form of electromagnetic wave, which might give you here a signal and might give you here a signal. And you can get rid of this by time gating due to the fact that the speed of light and the speed of the saw is significantly different. For us, that looks like this. We have here the electromagnetic crosstalk, and then for the, so this is detected here with the output IDT. We see our saw peak from our saw pulse. If we tune in resonance, we see the difference as seen before in terms of the surface acoustic wave transmission. And if you now look at the voltage probe here, we see similar things. We have this electromagnetic pickup here, but the saw out of resonance is not visible. And if we go in resonance, we see here this distinct feature of our saw pulse. So here we have the fully electrical detection of the response of our magnetization dynamics. You can analyze then this data again similarly as before, and notice that you have here your ferromagnetic resonance, and you can correlate this to your spin pumping signal, which shows the characteristic asymmetry. I also want to mention all the co-workers listed here from the Walter Schrotzky Institute, Lukas Rea and Martin Brandt for the SAW project, Mehdi Abdi and Michael Hartmann for the work on transmon and circuit nanomechanics, and of course the nanomechanics group of the Walter Meissner Institute and the magnetism group of the Walter Meissner Institute. And then I just leave you with my summary slide. So we have done sensing of magnetoelastics and driven ferromagnetic resonance with acoustics, and have also a spin pumping readout implemented here. Thank you very much for your attention.
Thanks very much. Any questions?
So I did not really understand the concept of this traveling wave. You mentioned the mode matching of the velocity of the surface acoustic wave being similar to the Magnon speed, but in your SMR measurements, does it really matter? Do you see some sort of effects of this traveling wave, of the sine wave, or is it more like a homogeneous FMR excitation?
So this is more like a homogeneous FMR excitation. If you go in the, if you think more in the direction of nanomechanics or optomechanics, then you would try to build resonators and a ferromagnetic entity. And for this, you want to have a most optimal mode overlap. That means that your standing wave of your excitation system or the standing wave of the SAW resonator or your optical resonator matches the excitation wavelengths or K-vector conservation of your excitation system to excite, like the magnetic system. And therefore, the kind of comparable velocities for speed of sound and magnons is an advantage, because you can compact and optimize your mode matching, your mode overlap in this scenario. For the kind of traveling waves here, it shouldn't matter.
Yes, I have two questions. The first one is that when you measure the restricted magnetic field in the first part, in the second part of the talk, you see also peak at zero fields.
Yeah, that's true. You're relating.
Yeah.
This is this kind of sharp feature here.
Exactly.
You notice that maybe it's here even better for the upsweep. This sharp feature comes if we come from negative fields and then go to positive fields. But at some point, your magnetization does a switching at the coercitive field, and this is what you see here in your signature.
So it's a consequence also of the...
It's a consequence of the magnetism. You're just you're basically having if you plot magnetization as function of field, that you kind of come and then you switch at some point, the classic hysteresis curve. And this is the kind of impact of this classic reorientation of the magnetization in the hysteresis curve, which you can also detect with your surface acoustic wave.
You said you had two questions.
Yes, the second one is actually simple. In the last part, you measure the current, and you transfer speeds to the platinum layer, and you measure the.
We measure the voltage drop at this.
Yes, it's actually important to have the width of the stripe smaller than the wavelength of the acoustic wave, but that doesn't matter. Actually, the polarity of the speeds you inject, does it depend on the phase of the acoustic?
No, what you have there. So this is actually the more complicated question. What you have there is you emit a. So what you do is you reduce your magnetization vector basically along this axis. And this is your excess angular momentum which you dissipate. And therefore it doesn't matter the phase relation at this point. The interesting thing is you could make this stripe technically thin and just kind of surf on a stripe width which is smaller than the wavelengths of your surface acoustic wave. That should be possible because the voltage that you generate here is proportional to the length of your stripe and not to the width. To a first instance, because you have seen that the pulses that we use here are reasonably high frequency pulses, so we do some 50 ohm magic with the circuitry there, and this makes things then maybe more complicated or more involved.
You were showing a graph with several harmonics.
Yeah.
So, have you noticed if the speed of sound changes with frequency? So if like the several harmonics are exactly 5 times the first harmonic, or the speed of sound changes a bit with the frequency?
I didn't, Matthias, do you still remember?
I think I didn't completely listen. So you're asking whether the ninth harmonic is exactly 9 times 107?
Yeah.
172? I think pretty much, yeah. So at least it was no concern to us when we calculated it. It might be off by a couple of megahertz.
I'm quite pleased that you don't see the third harmonic, because it's what you should expect.
We should see the third one, but there's bulk waves at that frequency that kind of like destroys the surface acoustic wave. So that's kind of like you see a lot of stuff where the third should be at some bulk waves.
Any other questions? Precisely 6 o'clock by that clock. So I think it's a good place to stop. So let's thank all 3 speakers for this session.